Imagine the universe as a vast darkened theater where the audience can't see the stage, but occasionally something explodes in the wings with such a terrible violence that the flash of it illuminates every single seat in the house. That's essentially our cosmic situation. We are sitting in the dark applauding the pretty twinkling lights, while backstage the great stellar catastrophes are rehearsing the performances that could end our entire show permanently. 66 million years ago, the dinosaurs learned this brutal lesson the hard way. As for us, we have built our entire civilization on the comfortable, naive assumption that space is mostly empty and mostly harmless. But the most recent discoveries suggest that we might be catastrophically and fatally wrong on both of those counts. The universe, it turns out, is neither empty nor is it silent. It is simply better at hiding than we are at seeking. Stay with me as we explore what the future holds for humanity. By the end of this journey, you will understand why the astronomers have started sleeping with one eye open, and why the most dangerous thing about our cosmic neighborhood is not what we can see that is approaching, but what we cannot. The dinosaur killer was just the beginning. 66 million years ago, something the size of a mountain fell from the deep darkness of space and ended the world as it was then known. The asteroid that carved out the Chicxulub crater was not just a rock. It was a cosmic reset button which was pressed with the force of 10 billion atomic bombs. Picture this, a 10 to 15 kilometer wide chunk of a space debris that was hurtling through the void at a staggering 20 kilometers per second, and that suddenly encountered our blue fragile marble. In a matter of milliseconds, it excavated a crater that was nearly 200 kilometers across in what we now call the Yucatan Peninsula. The impact released an energy that was equivalent to 100 million megatons of TNT, which is roughly 2 million times more powerful than the largest nuclear weapon that was ever detonated. But the explosion, the initial blast, was just the beginning of the horror. Within hours, a wall of a molten rock and a superheated debris rained down across the entire North American continent. The tsunamis that were taller than the modern skyscrapers swept across the continents. The real killer, though, was what came next in impact winter that lasted for years. Imagine the sky that is turning black, not for the days or the weeks, but for the months on end. The sunlight could not penetrate the thick, choking blanket of a dust and a soot that circled the entire globe. Without a photosynthesis, the plants died. Without the plants, the herbivores starved. Without the herbivores, the carnivores followed. The entire food chain collapsed like a line of dominoes, taking 75% of all of the species with it, including every single non-avian dinosaur on the entire planet. The terrifying truth is this: the scientists today use the Chicxulub impact as their baseline for a cosmic catastrophe, not because it represents the worst that could possibly happen, but because it is simply the most recent example that we can study in a detail. What keeps the planetary defense experts awake at a night is not just the memory of what happened 66 million years ago. It is the certain knowledge that something much, much bigger could be coming. Here is where the things get unsettling. The long-period comets, those icy, ghostly wanderers from the outer reaches of our solar system, can appear with a virtually no warning at all. While we have gotten remarkably good at tracking the asteroids, the comets are the different beasts entirely. They originate in the Oort cloud, a vast spherical shell of a frozen debris that extends nearly halfway to the nearest star. When the gravitational nudges send one of these great ice balls hurtling toward the inner solar system, we might have only the months or the years to spot it, to analyze its trajectory, and if it is necessary to attempt to deflect it. The NASA's DART mission proved that we can nudge the small asteroids off a course. In 2022, the spacecraft successfully altered the orbit of the Dimorphos, a small moon that was orbiting the asteroid Didymos. But the comets present the unique challenges that make them far more difficult targets. They are traveling faster than the asteroids when they reach the Earth's neighborhood, sometimes twice as fast. They are also more fragile, which are composed of a loosely bound ice and a rock that could fragment under the stress of the deflection attempts. And unlike the asteroids, which follow the predictable paths, the comets develop the tails and experience the non-gravitational forces as they heat up near the sun, which is making their trajectories harder to predict with a precision. The modern sky surveys like the Atlas, the Pan-STARRS, and the Zwicky Transient Facility are scanning the heavens nightly, catching more potentially hazardous objects than ever before. These automated sentinels have revolutionized our ability to spot the incoming threats, but they are not infallible. The objects that are approaching from the direction of the sun remain largely invisible until they are uncomfortably close. The southern hemisphere's coverage, while it is improving, still lags behind the northern surveys. The distinction between the asteroids and the comets matters more than you might think. The asteroids are primarily a rock and a metal, a solid, a predictable, and a relatively easy to track once they are discovered. The comets, on the other hand, are the cosmic snowballs that become increasingly active as they approach the sun. The solar heating causes their icy surfaces to sublimate, creating the spectacular tails that we admire, but also the jets of a gas that can alter their trajectories in the ways that are difficult to predict. And even more sobering is the scale that we are dealing with. The Chicxulub impactor, as devastating as it was, measured only 10 to 15 kilometers across. But we now know that much larger comets exist. In the past decade, we have confirmed the existence of the comet nuclei that are measuring over 100 kilometers in a diameter, the objects that would make the dinosaur killer look like a pebble by a comparison. And then there are the truly unknown quantities, the interstellar visitors. In 2017, we got our first confirmed look at an object that was not born in our solar system when the ʻOumuamua streaked through the inner solar system. 2 years later, the comet Borisov followed a suit. These interstellar wanderers reminded us that a space is not empty and that the visitors from the other star systems pass through our cosmic neighborhood more frequently than we had previously imagined. As we peer deeper into a space with the increasingly sophisticated instruments, we are beginning to comprehend the true inventory of the objects that could theoretically find their way to the Earth. The sobering reality is that if the Chicxulub impact was just a warm-up act, then the main event could be something that is far more catastrophic than anything that our species has ever witnessed. What happens when the cosmos decides to throw something that is truly massive our way? The great comets of a history. Some of the comets do not just visit our skies, they dominate them. These are the great comets, the ones that burn themselves into a human memory and remind us that we share our solar system with some truly spectacular and a potentially terrifying wanderer. Take the Hale-Bopp, the superstar of 1997. For 18 months, an almost unprecedented length of a time, this cosmic visitor was visible to the naked eye, casting an eerie glow across the Earth's night sky. What made the Hale-Bopp so special was not just its brightness, but its sheer size. With a nucleus that was estimated at 60 kilometers across, it was a genuine giant among the comets. As it approached the sun, its coma, the glowing envelope of a gas and a dust that was surrounding the nucleus, expanded to nearly 4 million kilometers in a diameter which was larger than the sun itself. But the Hale-Bopp was not just a scientific marvel, it was a cultural phenomenon. The millions of the people stepped outside to witness what many of them described as the most spectacular comet of their lifetimes. Yet beneath the wonder lay an undercurrent of an unease. Here was a visible proof that the enormous objects from the outer solar system could appear in our cosmic neighborhood with a relatively little warning. The Hale-Bopp had been discovered only 2 years before its closest approach to the sun, a cosmic blink of an eye. The history is filled with such unexpected visitors. The Great Comet of 1811, which was sometimes called the Napoleon's Comet, blazed across the European skies for the months. With a coma that was larger than the sun and a tail that was stretching 60 degrees across the sky, it was impossible to ignore. The superstitious observers linked its appearance to the military campaigns that would lead to the Napoleon's downfall in Russia. While we now know better than to attribute the earthly events to the celestial visitors, the comet's timing seemed almost ominous to those who had witnessed it. These great comets share the certain characteristics that both fascinate and unsettle the astronomers. They often experience the dramatic brightening events that are called the outbursts, where the nucleus suddenly becomes more active and ejecting the massive amounts of a material and causing the comet to flare in a brightness by the factors of the hundreds or even the thousands. These outbursts are unpredictable and poorly understood, reminding us how little we truly know about the behavior of these icy time capsules from the early solar system. The eerie green glow that many of the comets display, which are including some of the recent visitors, has sparked the countless conspiracy theories and an alien speculation. The reality is both more mundane and more beautiful. That ghostly green light comes from the diatomic carbon molecules and a cyanogen fluorescence, a simple chemistry that is occurring as a solar radiation energizes the comet's coma. It is not an alien technology or a toxic gas. It is the same carbon that forms the backbone of all of a life on the Earth, glowing in the vacuum of a space. Yet the sudden appearance of these great comets continues to humble the astronomers. Before our current generation of the automated sky surveys, most of the comets were discovered by the amateur observers or were stumbled upon by an accident. Even today, with our sophisticated detection networks, we occasionally get surprised by the comets that seem to appear from a nowhere, already bright enough to see with the naked eye. The geometry of the comet encounters plays a crucial role in both their spectacular appearance and their potential threat level. A comet's perihelion at its closest approach to the Sun determines how much a solar heating it experiences. More heating means more outgassing, which creates the larger, more spectacular tails, but also makes the comet's trajectory less predictable. Some of the comets, like the Atlas C 2019 Y4, literally fall apart under this thermal stress, fragmenting into the multiple pieces as they round the Sun. What makes these historical great comets particularly unsettling from a planetary defense perspective is their reminder that the large, active objects regularly enter the inner solar system. While their spectacular tails and their bright appearance make them to seem threatening, it is important to remember that a visibility does not equal a danger. A comet's brightness depends on its size, its composition, its distance from both the Sun and the Earth, and a viewing geometry. A relatively small comet that is passing close to the Earth might appear to be brilliant, while a much larger one that is passing at a greater distance might barely be visible. Throughout a history, the comets have served as the harbingers of a doom in the human cultures that were worldwide. The ancient Chinese astronomers meticulously recorded the comet appearances, often and interpreting them as the omens of a dynastic change. The medieval Europeans saw them as the signs of a divine displeasure, the harbingers of a plague, a war, or a famine. While we have outgrown such superstitions, there is something primal about the fear that these visitors inspire perhaps an evolutionary memory of the genuine cosmic threats that our ancestors had witnessed. The anthropological connection between the comets and a catastrophe is not entirely misguided. While most of the comets pose no threat to the Earth, they serve as the visible reminders that a space is not empty, that the objects from the outer reaches of our solar system can and do venture into our cosmic neighborhood. Each great comet that we witness is essentially a preview of the kinds of the objects that populate the distant Oort cloud, a vast reservoir of the potential visitors that we are only beginning to understand. As we will see, some of these visitors are not even the natives of our solar system, and if a surprise is what makes the great comets so unsettling, then what should we make of the visitors that are not even bound to our Sun? The alien visitor 3I Atlas 2025 has given us something that is unprecedented, a confirmation of the third known interstellar object to visit our solar system. It was designated as the 3I Atlas, or more formally as the C 2025 A3, and this cosmic wanderer has earned the distinction of being only the third confirmed visitor from beyond our solar system, following the mysterious ʻOumuamua in 2017 and the comet Borisov in 2019. What makes an object an interstellar is not just where it came from, but where it is going. Unlike the comets and the asteroids that were born in our solar system, which follow the elliptical orbits that are bound to the Sun, the interstellar objects travel on the hyperbolic trajectories. In a simple term, they are moving so fast that our Sun's gravity can bend their path, but cannot capture them. They swing through our solar system once and then continue into the void, never to return. The media has latched on to the 3I Atlas's glowing green appearance, with some of the outlets that are breathlessly speculating about an alien technology. The reality is far more prosaic, but no less fascinating. That eerie green glow is almost certainly the same phenomenon that we see in the ordinary comets, a fluorescence from the diatomic carbon and the cyanogen molecules that are energized by a solar radiation. It is not an evidence of an extraterrestrial engineering. It is an evidence that an interstellar space contains the same basic building blocks of a chemistry that we find throughout our own solar system. The 3I Atlas reached a perihelion, its closest approach to the Sun, on October 29, 2025, at a distance of roughly 2.5 astronomical units, which is placing it beyond the orbit of Mars. This timing provided the astronomers with a precious opportunity to study an interstellar visitor during its period of a maximum activity, when a solar heating would cause it to outgas most vigorously and reveal the clues about its composition. For the scientists, the 3I Atlas represents a unique laboratory, a chance to compare the composition and the behavior of an object that was formed around another star with the comets that were native to our own solar system. The questions that they are asking are profound. Do the interstellar comets contain the same mix of the ices and the organic compounds as our local comets? How do the stellar nurseries in the different parts of the galaxy differ in their chemistry? What can this visitor tell us about the conditions that existed when and where it was formed, possibly the billions of the years ago? The discovery of the 3I Atlas follows a now familiar pattern. The automated survey systems like the Atlas, the Asteroid Terrestrial Impact Last Alert System, first spotted what appeared to be a routine comet or an asteroid. But the follow-up observations revealed something that was extraordinary. The object's trajectory was hyperbolic, which was indicating that it was moving too fast to be gravitationally bound to our solar system. A confirmation required the multiple observations over the several weeks, tracking the object's precise path through space to eliminate any possibility of a measurement error. Here is what should keep you awake at a night. If we have detected the 3 interstellar objects in less than a decade, then how many of the fainter ones have passed through unnoticed? Our current detection capabilities are biased toward the objects that are either large, highly reflective, or actively outgassing. A dark, inactive interstellar asteroid, particularly one that is approaching from the direction of the Sun, could easily slip past our surveys entirely. The speed of the interstellar objects presents the unique challenges for a planetary defense. The 3I Atlas, like its predecessors, is traveling at roughly 30 kilometers per second relative to the Sun, which is significantly faster than the typical solar system objects. At these velocities, even if we detected a dangerous interstellar object years in advance, deflecting it would require the fundamentally different techniques than those that are being developed for the conventional asteroids and the comets. But let's address the elephant in the room, the persistent speculation about an extraterrestrial technology. The NASA, the ESA, and other space agencies maintain that all of the 3 confirmed interstellar objects are consistent with the natural phenomena. However, they are also taking these claims seriously enough to study each visitor with an unprecedented intensity. The scientific method demands that we examine all of the possibilities, even the exotic ones, while maintaining an appropriate skepticism. The ʻOumuamua controversy illustrates this balance perfectly. When the object exhibited a slight non-gravitational acceleration, a speeding up in the ways that could not be explained by gravity alone, some of the researchers proposed the exotic explanations that were ranging from the light sails to the alien probes. The mainstream scientific community, however, has converged on the more conventional explanations, an outgassing of a hydrogen or sublimating the organic compounds, creating the tiny thrusts, or even the radiation pressure from the Sun that was acting on an unusually shaped object. The comet Borisov, by contrast, behaved exactly like a typical comet, which was complete with a normal coma and a tail. Its composition, as it was revealed by a spectroscopic analysis, closely matched that of the comets from our own Oort cloud, which was suggesting that the basic processes of a planetary formation and a comet composition may be the universal features of the stellar systems. What makes the 3I Atlas particularly intriguing is that it appears to be exhibiting a typical cometary activity, while clearly being an interstellar visitor. This gives the astronomers the best of both of the worlds, a chance to study an alien object that is displaying a familiar behavior and allowing for a direct comparison with our solar system's native population. The implications extend beyond pure science. These interstellar visitors are attesting our detection and response capability, the same systems that we are developing to protect the Earth from the conventional threats. Every hyperbolic trajectory that we track, every composition measurement that we make, and every behavioral quirk that we catalog is an improving our ability to distinguish between the natural phenomena and the potentially artificial objects. The uncomfortable truth is that if the interstellar visitors are common enough for us to detect the three in less than a decade, then they are probably far more common than we had previously imagined. Most of them are likely too small, dark, or inactive to detect with the current technology. But as our survey capabilities improve, we should expect to find more of these cosmic travelers that are passing through our celestial neighborhood. And if the alien snowballs are indeed a regular occurrence, then what about the alien ice mountains? What might be lurking in an interstellar space that we have not yet learned to see? The monster is approaching Bernardinelli Bernstein. In the catalog of the cosmic nightmares, few objects inspire quite the same mixture of a fascination and a dread as the C-2014 UN-271, which is better known as the comet Bernardinelli Bernstein. It was discovered in 2021 through a painstaking analysis of the dark energy survey data, and this object holds the distinction of being the largest comet nucleus that was ever measured, a cosmic monster that is stretching approximately 137 kilometers across. To put that size in a perspective, imagine a mountain range that is floating through a space. Most of the comet nuclei measure just a few kilometers in a diameter, the dirty snowballs that could fit comfortably within a major city. The Bernardinelli Bernstein is different. At 137 kilometers across, it is larger than a Rhode Island. Its volume is roughly 1 million times greater than a typical comet, containing enough of an ice and a rock to fill a significant fraction of the Earth's oceans if it was melted. The discovery story itself reads like a detective novel. The astronomers Pedro Bernardinelli and Gary Bernstein were mining through the years of the archived data from the Dark Energy Survey, a project that was primarily focused on mapping the universe's large-scale structure. Hidden in those images that were recorded between 2013 and 2019 was something that was unexpected, a slowly moving object in the outer solar system. The additional observations confirmed what the data suggested. This was no ordinary trans-Neptunian object, but a comet of an unprecedented size. When the Bernardinelli Bernstein reaches a perihelion in 2031, it will approach within 10.9 astronomical units of the Sun, which is still well beyond the Saturn's orbit and posing absolutely no threat to the Earth. But that distance masks the truly terrifying aspect of this object. It is a preview of what might be lurking in the outer reaches of our solar system. The Hubble Space Telescope and other instruments have confirmed the comet's enormous size through a careful thermal modeling. As the Bernardinelli Bernstein slowly approaches the Sun, a solar heating causes its surface ice to sublimate, creating a measurable coma. By analyzing the brightness and the thermal emission of both the nucleus and its surrounding envelope, the astronomers calculated that the solid nucleus itself spans roughly 137 kilometers, which is making it not just the largest comet that was ever observed, but possibly the largest object in the Oort cloud. Here is where the mathematics become sobering. If an object like the Bernardinelli Bernstein were to impact the Earth, and let's be absolutely clear that this particular comet poses no such threat, the consequences would be literally unimaginable. The kinetic energy of a 137-kilometer object, which is traveling at the typical comet speeds, would be roughly 1,000 times greater than the Chicxulub impact that ended the age of the dinosaurs. Such an impact would represent a civilization-ending event of the highest order. The explosion would excavate a crater that was several hundred kilometers across and instantly vaporizing everything that was within the thousands of the kilometers of the impact site. The atmospheric shock would trigger the global earthquakes and the volcanic eruptions, the seismic events that were so powerful that they would literally crack the planet's crust. The ocean impacts would generate the tsunamis that would scour the continents clean. The long-term climate effects would make the post-Chicxulub impact winter look mild by a comparison. But let's step back from the nightmare scenario and focus on what the Bernardinelli Bernstein actually teaches us. Its existence proves that the genuine giants inhabit the Oort cloud, the vast spherical shell of an icy debris that surrounds our solar system. This distant reservoir that is extending roughly halfway to the nearest star contains the remnants of our solar system's formation 4.6 billion years ago. Most of its contents remain frozen and invisible, but occasionally the gravitational perturbations send the objects that are tumbling toward the inner solar system. The discovery of the Bernardinelli-Bernstein suggests that our understanding of the Oort cloud's population has been incomplete. If the objects that are this large exist, and remember that this one was only discovered because it happened to pass through the relatively narrow field of view of one particular survey, then how many of the others remain undetected in the outer darkness? From a planetary defense perspective, the objects like the Bernardinelli-Bernstein present the unique challenges. Their immense size would make them virtually impossible to deflect by using a current or a planned technology. The kinetic impactors like the DART mission would be ineffective against such massive targets. The nuclear explosives might fragment them, but the resulting debris field could pose an even more widespread threat than the original intact object. The most realistic defense would be an early detection and an evacuation, and assuming that we had the decades or the centuries of a warning. Fortunately, the orbital mechanics of the long-period comets work in our favor for a detection. The objects, like the Bernardinelli-Bernstein, take the millions of the years to complete their journeys from the outer Oort cloud to the inner solar system. Unlike the potentially hazardous asteroids, which might be discovered only the months or the years before a close approach, the true long-period comets can be detected the decades before they reach a dangerous proximity to the Earth. The upcoming Vera C. Rubin Observatory promises to revolutionize our ability to detect such objects. When it begins the operations, this facility will survey the entire visible sky every 3 nights, detecting the moving objects far more efficiently than the current surveys. The computer models suggest that it could increase our discovery rate of the long-period comets by the orders of a magnitude A, finally A, giving us a comprehensive inventory of what is lurking in the outer solar system. The media coverage of the Bernardinelli-Bernstein illustrates both the opportunities and the dangers of a science communication in the digital age. The headlines often emphasize the object's enormous size, while downplaying the fact that it poses no threat to the Earth. This creates a challenging balance for the scientists. How do you convey the genuine scientific significance of such discoveries while avoiding an unnecessary public alarm? The answer lies in a context and an education. The Bernardinelli-Bernstein is remarkable precisely because it is so rare. Its enormous size makes it a unique laboratory for studying the composition and the structure of the pristine solar system materials. Its predictable trajectory gives the astronomers the years to plan the detailed observations. Its distance ensures that we can study it safely without any risk to the Earth. Yet the deeper implication remains unsettling. If a 137-kilometer comet can exist, then what is the upper limit? How big do these cosmic monsters get? The hypothetical doomsday comets. Let's venture into the realm of a pure speculation, the kind of a scenario that keeps the planetary defense specialists staring at the ceiling at 3 in the morning. Imagine, if you will, the 2 hypothetical comets, the Thanos, which is measuring 300 kilometers across, and the Leviathan, a 500-kilometer monster that dwarfs even the Bernardinelli-Bernstein. These are the thought experiments, not the real objects, but they represent the kinds of the cosmic nightmares that could theoretically exist in the outer reaches of our solar system. The Thanos, a hypothetical 300-kilometer comet, would contain roughly 27 times more mass than the Bernardinelli-Bernstein. If such an object were to impact the Earth, and remember that we are firmly in the realm of a speculation, here the consequences would transcend anything in the Earth's recorded geological history. The impact would release an energy that was equivalent to roughly 100 million megatons of TNT, creating a crater that was over 1,000 kilometers across, and triggering the earthquakes that would register a magnitude 10 or a higher on the Richter scale, the seismic events that were so powerful that they would literally crack the planet's crust. But the Leviathan, our 500-kilometer hypothetical monster, would make even the Thanos look modest. An impact from such an object would release an energy that was comparable to the formation of the Earth's moon, the kind of a collision that the planetary scientists believe occurs perhaps once in a solar system's entire history. We are talking about the forces that could literally blow away the Earth's atmosphere and boil the oceans into a space. Here is a crucial point that often gets lost in the sensationalist discussions. A size alone does not determine the orbital mechanics. Even a 500-kilometer comet would not gravitationally destabilize the Earth's orbit unless it passed absurdly close within a few Earth radii. The real danger from such objects is not a gravitational disruption, it is the catastrophic release of a kinetic energy upon an impact. The physics of a comet deflection becomes meaningless at these scales. The current planetary defense strategies rely on delivering the relatively small amounts of an energy to slightly alter an object's trajectory over a time, the principle that was demonstrated by the NASA's successful DART mission. But the kinetic impactors would be utterly useless against the objects that were this massive. Even the nuclear explosives, which were often proposed as the last resort deflection tools, would be like trying to stop a freight train with a firecracker. This is where the volatile nature of the comets becomes both a blessing and a curse. Unlike the solid metallic asteroids, the comets are the loosely bound collections of an ice, a rock, and the organic compounds. The same thermal stress and an outgassing that makes them spectacular could also make them prone to a fragmentation. In a theory, a precisely targeted nuclear explosion might break up a large comet, but the resulting debris field could pose an even more widespread threat than the original intact object. The detection timeline for such massive objects would be both our salvation and our torment. The objects that were this large would be visible to our current surveys the decades before reaching the inner solar system and assuming that they approach from a favorable direction. But a confirmation of their trajectories and a threat assessment would take the months or the years, during which a public panic could become as destructive as the cosmic threat itself. Here is where our current blind spots become particularly concerning. Most of our asteroid and comet detection systems are located in the northern hemisphere, creating the gaps in the southern hemisphere's coverage. The objects that are approaching from the direction of the sun remain largely invisible until they are uncomfortably close, and the comets that are arriving from the high inclination orbits that are above or below the plane of the solar system might evade a detection until relatively late in their approach. The upcoming Vera C. Rubin Observatory will dramatically improve our detection capabilities, scanning the entire visible sky every 3 nights and cataloging the moving objects with an unprecedented efficiency. The computer models suggest that it will detect the hundreds of the thousands of the new asteroids and the comets, finally giving us a comprehensive census of the potentially hazardous objects in our cosmic neighborhood. But even the most sophisticated surveys cannot eliminate every blind spot. The comets can experience the dramatic changes in a brightness due to an outgassing and the fragmentation events. An object that appears to be small and harmless might suddenly flare to many of the times its original brightness, revealing a much larger nucleus than was initially estimated. Conversely, a large comet might appear to be deceptively faint if its surface becomes covered with the non-volatile materials that suppress an outgassing. The timescales that were involved in the hypothetical mega-comet encounters would be both a blessing and a curse. While we might have the decades of a warning, the public psychological impact could be devastating. Imagine learning that a civilization-ending object was approaching the Earth with a mathematical certainty. How would the governments respond? How would the markets react? Would an international cooperation prevail? Or would the nations turn inward in a preparation for a catastrophe? The uncomfortable truth is that our planetary defense capabilities, while they are improving rapidly, remain woefully inadequate for the truly massive threats. We are developing the techniques that might work against the city-killer asteroids, the objects that are tens to the hundreds of the meters across. We have demonstrated our ability to deflect the small asteroids like the Dimorphos. But against the hypothetical giants like the Thanos or the Leviathan, our best defense would be an early detection that was followed by a mass evacuation, the underground shelters, and the long-term survival preparations. These scenarios force us to confront the limits of a human technological capability. We are quite literally one cosmic accident away from an extinction. The only comfort, and it is a cold comfort indeed, lies in the mathematical improbability of such events that are occurring within the human timescales. The larger the potential impactor, the rarer it becomes. Yet the universe has already demonstrated its capacity for the shocking surprises. Who had predicted the existence of the interstellar visitors like the ʻOumuamua? who had anticipated a finding, a 137-kilometer comet like the Bernardinelli Bernstein. As our surveys become more sensitive and comprehensive, we are discovering that the solar system contains more large objects than the previous models had predicted. If the ice mountains like these represent the extreme end of the solar system's threats, then what other predators might be lurking in the cosmic dark? The objects that make even the 500-kilometer comets look like the harmless dust motes. The invisible killers, the rogue black holes. Somewhere in the darkness that is between the stars, the invisible predators drift through our galaxy like the cosmic sharks, the stellar mass black holes that have been ejected from their birth systems and now wander freely through an interstellar space. Until recently, these rogue black holes existed primarily in the computer simulations and the theoretical papers. But in 2022, the Hubble Space Telescope gave us our first confirmed glimpse of one of these invisible killers. The discovery came through a gravitational microlensing, a phenomenon that Einstein had predicted, but he never expected that we would be able to observe directly. When a massive object passes between the Earth and a distant star, its gravity acts like a lens, temporarily magnifying the star's light. For 6 years, the Hubble tracked one such event, watching as an invisible object's gravity distorted the light from a star that was 25,000 light-years away. The meticulous analysis that followed revealed something that was extraordinary. A black hole that was roughly 7 times the mass of our Sun, drifting alone through the galaxy at about 45 kilometers per second. This was not just an academic curiosity, it was a proof that our worst cosmic fears might be justified. The astronomers estimate that there are approximately 100 million stellar mass black holes that are scattered throughout the Milky Way, most of them completely invisible, which are detectable only when they happen to pass between us and the more distant light sources. The vast majority of them remain hidden in the darkness, following the trajectories that we cannot predict, carrying enough of a gravitational influence to disrupt the planetary systems if they pass too close. But what does too close actually mean? When we are talking about the rogue black holes, the mathematics are both reassuring and terrifying. A stellar mass black hole would need to pass within roughly 1,000 astronomical units of our solar system, about 25 times the distance to the Pluto, to significantly perturb the Earth's orbit. At that distance, its tidal forces would begin stretching and compressing our planet's crust, triggering the massive earthquakes and the volcanic eruptions long before it actually captured the Earth or flung us into an interstellar space. The odds of such an encounter are mercifully small, roughly comparable to winning the lottery several times in a row. But the consequences would be absolute. Unlike the asteroid impacts, which might destroy a civilization but leave the planet intact, a close encounter with a rogue black hole would fundamentally alter the Earth's position in the solar system, making our world uninhabitable for the billions of the years. The discovery of that first confirmed rogue black hole has revolutionized our understanding of galactic demographics. The computer models suggest that these objects are created during the violent supernova explosions that mark the deaths of the massive stars. If the explosion is asymmetric, if more material gets ejected in one direction than another, then the newborn black hole receives a natal kick that can accelerate it to the hundreds of the kilometers per second, which is fast enough to escape its parent star system entirely. Some of these cosmic refugees have been wandering the galaxy for billions of years, the invisible hitchhikers that are carried along by the Milky Way's rotation, but are not gravitationally bound to any particular star system. They are the fossils of the ancient stellar catastrophes, the black holes that witnessed the galaxy's youth, and have been drifting through a space since before our solar system even existed. The detection challenge is immense. The black holes do not emit a light, they absorb it. The only way to find the isolated black holes is through their gravitational effects, the microlensing events like the one that the Hubble observed, or the gravitational waves that they produce when they collide with other massive objects. The upcoming Nancy Grace Roman Space Telescope will dramatically improve our microlensing capabilities, potentially revealing the thousands of the additional rogue black holes that are currently hidden in our galactic neighborhood. But here is where the story takes an unsettling turn. The black hole that the Hubble discovered was not the largest or the most dangerous of its kind. It was simply the first one that we had happened to catch in the act of lensing a background star. The recent discoveries suggest that the population of the massive stellar remnants that are wandering our galaxy might be far larger and more diverse than we had previously imagined. Consider the BH3, which was discovered in 2024 through an analysis of data from the European Space Agency's Gaia mission. This stellar mass black hole that was located just 2,000 light-years from the Earth weighs in at roughly 33 solar masses, which is making it the most massive stellar black hole that was found in our galaxy. Unlike the isolated rogue black hole that was detected by the Hubble, the BH3 has a companion star, which is what made its discovery possible. But its enormous mass raises the uncomfortable questions about how many of the similar giants might be drifting unseen through an interstellar space. The physics of the black hole encounters becomes increasingly surreal as we consider the closer approaches. At the distances of a few dozen astronomical units, roughly the scale of our outer solar system, a rogue black hole would not just perturb the planetary orbits, it would begin shredding the outer planets themselves through the tidal forces. The Jupiter's moons would be scattered like the pool balls, the Saturn's rings would be twisted into the spirals before being consumed entirely. And even more disturbing is the realization that we might not see such an intruder that is coming. Unlike the comets, which brighten as they approach the sun, the black holes remain invisible until they are close enough for their gravitational effects to become apparent. By the time that we detected the orbital perturbations of the outer planets, the rogue black hole might be close enough that an evacuation would be impossible and a deflection would be unthinkable. The Roman Space Telescope, which is scheduled for a launch in the mid-2020s, represents our best hope for cataloging these invisible threats. Its wide-field infrared camera will monitor the hundreds of the millions of the stars simultaneously, watching for the telltale signs of the micro-lensing events that reveal the hidden massive objects. The computer simulation suggests that it might detect the dozens of the rogue black holes per year, finally giving us a statistical understanding of how many of these objects populate our galactic neighborhood. Yet even the improved detection capabilities cannot eliminate the fundamental uncertainty. We are essentially playing a cosmic game of hide-and-seek with the invisible objects that could end a human civilization without a warning. The universe contains the billions of the stellar mass black holes, most of them completely dark, following the trajectories that were shaped by the gravitational interactions that occurred long before the Earth existed. What keeps the astronomers awake is not the certainty of a catastrophe. The odds remain vanishingly small. It is the knowledge that somewhere in the darkness that is between the stars, the invisible predators are drifting through space, carrying enough of a gravitational influence to reshape the solar systems. We have finally proven that they exist, but we have barely begun to understand how many of them are out there, where they are going, or when one of them might wander close enough to remind us how fragile our cosmic situation really is. And if the lone stellar mass black holes represent the small fry of a cosmic predation, then what about the supermassive beast that lurks at the very heart of our own galaxy, the supermassive hunger? At the center of our galaxy lies a monster that is so massive that it defies comprehension. The Sagittarius A, a supermassive black hole that is weighing roughly 4 million times as much as our Sun. For most of human history, this cosmic leviathan remained hidden behind the clouds of dust and gas, which were invisible to the optical telescopes, but betraying its presence through the frenzied dance of the nearby stars. In 2022, the Event Horizon Telescope finally gave us our first direct image of this galactic predator, revealing the glowing ring of a superheated matter that was spiraling toward an oblivion at its event horizon. To put the Sagittarius A's mass in a perspective, imagine trying to compress the 4 million suns into a region that was smaller than the Mercury's orbit. The gravitational field is so intense that a matter that is orbiting near the event horizon reaches the speeds that are approaching 20% of a light speed before vanishing forever. The stars that venture too close are torn apart by the tidal forces in the spectacular events that are called the tidal disruption flares their stellar material that is forming the brilliant accretion disks before disappearing into the void. But here is what should provide some of a comfort. The Sagittarius A currently poses no direct threat to the Earth. At roughly 26,000 light-years from our solar system, we are safely nestled in the galactic suburbs, far from the chaos that surrounds our galaxy's central engine. The black hole is not going to suddenly wake up and vacuum the Earth into its maw like some cosmic drain cleaner. The black holes do not work that way. They are not the cosmic vacuum cleaners that are indiscriminately sucking up a nearby matter. However, the Sagittarius A has not always been the relatively quiet giant that we observe today, and evidence suggests that it experienced the periods of an intense activity in the recent cosmic past, the episodes that painted our galaxy in a high-energy radiation and left the traces that we can still detect today. The most striking evidence comes from the Fermi Gamma Ray Space Telescope, which revealed the enormous bubbles of an energized gas that were extending 50,000 light-years above and below the galactic plane. These Fermi bubbles are the cosmic equivalent of the exhaust plumes, the remnants of the Titanic outbursts that occurred roughly 2 to 4 million years ago. What could cause such violent episodes? The answer lies in the feeding habits of the supermassive black holes. Currently, the Sagittarius A exists in a relatively starved state. There simply is not much of a nearby matter for it to consume. But occasionally, the gas clouds, the disrupted stars, or even the smaller black holes fall into its gravitational well, providing a fuel for the spectacular outbursts. When a supermassive black hole feeds actively, it does not just grow larger, it becomes a quasar, one of the most luminous objects in the universe. Imagine if the Sagittarius A suddenly transitioned from its current dormant state to a full quasar mode. The radiation output would increase by the factors of the thousands or the millions. While the Earth's distance provides a significant protection, such an outburst would still bathe our solar system in the unprecedented levels of a high-energy radiation. The immediate effects would be largely invisible. The cosmic rays and gamma radiation do not produce the spectacular light shows in the Earth's atmosphere, but over a time, the increased radiation could affect our planet's climate and an atmospheric chemistry in the subtle but potentially a significant way. The mechanics of such outbursts involve a physics that pushes the boundaries of a human understanding. As a matter spirals toward the black hole, it forms an accretion disk that heats to the billions of the degrees. The magnetic field lines that are threading through this disk can launch the jets of a material at a near-light speed, creating the focused beams of an energy that stretch across the thousands of the light years. If the Earth happened to lie along one of these jet directions during an active phase, the consequences could be far more severe than the diffuse radiation from a typical quasar outburst. The recent observations that were using the Event Horizon Telescope have revealed that the Sagittarius A is already showing the signs of a structure in its immediate environment. The polarized light observations suggest the complex magnetic field configurations that are around the black hole, the same kinds of the fields that could, under the right conditions, launch the powerful jets. While the black hole remains relatively quiet today, these magnetic structures indicate that it retains the potential for a much more dramatic activity. The timescales that were involved in a supermassive black hole's variability span from the minutes to the millions of the years. The Sagittarius A exhibits the small-scale flaring on the timescales of the hours as the small amounts of a matter cross the event horizon. But the major outbursts that created the Fermi bubbles occur over the much longer periods, the sustained feeding episodes that might last the hundreds of the thousands of the years. What triggers these major episodes remains an active area of research. The computer simulations suggest the several possibilities: the disruption of the massive star clusters that are near the galactic center, the capture of the intermediate mass black holes, or the collision of the gas-rich smaller galaxies with our own. Any of these events could dump the enormous amounts of material into the Sagittarius A's gravitational well, potentially triggering another quasar-like outburst. The psychological impact of living with a 4 million solar mass black hole at the center of our galaxy is fascinating to consider. For most of human history, we were completely unaware of its existence. Now that we know that it is there, now that we have actually photographed its shadow, how should that knowledge affect our cosmic perspective? We are essentially living in a galaxy with a loaded gun at its center, one that could theoretically fire at any moment. Yet this knowledge also provides a strange form of comfort. The Sagittarius A has existed in roughly its current state for billions of years. Our solar system has orbited the galaxy the dozens of the times during this period and experiencing whatever radiation environment the central black hole creates. A life on the Earth has evolved under these conditions. In a very real sense, we are adapted to living in a galaxy with an active galactic nucleus. The real uncertainty lies not in whether the Sagittarius A might become active again. It almost certainly will, given enough of a time, but in when such an activity might occur and what a form it might take. The black hole operates on the cosmic timescales that dwarf a human civilization. An outburst that seems to be sudden from a galactic perspective might unfold over the thousands of the human generations. A modern astronomy has given us the tools to monitor our galactic center with an unprecedented precision. The radio telescopes track the orbits of the stars that are close to the Sagittarius A, watching for the signs of a disruption that might herald an increased activity. The X-ray and the gamma-ray satellites monitor the black hole's current output, looking for the changes that might indicate the beginning of a more active phase. But perhaps the most unsettling aspect of the Sagittarius A is not its potential for the future outbursts. It is the reminder that our entire galaxy is, in a very real sense, organized around this supermassive predator. Every star in the Milky Way, which are including our Sun, follows an orbit that is ultimately determined by the gravitational influence of this central monster. We are not just living near a supermassive black hole, we are living in a gravitational system that exists because of it. If the sleeping giant at our galaxy's heart represents a distant threat, then what about the cosmic phenomena that could reach across an intergalactic space to remind us that the universe contains the even larger predators, the other cosmic giants? Beyond the black holes lurk the other cosmic giants that are capable of unleashing a destruction across the galactic distances, the stellar phenomena that are so energetic that they can be detected from the billions of the light years away. These are the universe's heavy artillery, the neutron star collisions, the magnetars, and the gamma-ray bursts that release more energy in a second than our Sun will produce over its entire 10 billion-year lifetime. On August 17, 2017, humanity witnessed something that was unprecedented, the collision of the two neutron stars that were detected simultaneously by the gravitational wave observatories and the optical telescopes. The event that was designated as the GDU 170817 marked the dawn of a multi-messenger astronomy, our first glimpse of a cosmic catastrophe through both the ripples that it created in a spacetime and the light that it produced. The neutron stars represent a matter that is compressed to the unimaginable densities, the objects where a teaspoon of a material would weigh as much as a Mount Everest. When the two such objects spiral into each other over the millions of the years, the final merger releases the gravitational waves that stretch and compress a space itself as they race outward at a light speed. But the electromagnetic fireworks are equally spectacular. The collision creates a kilonova, an explosion that outshines the entire galaxies for the weeks and forges the heavy elements like a gold, a platinum, and a uranium in the quantities that dwarf the production of an ordinary stellar nucleosynthesis. The gold in your jewelry, the platinum in your car's catalytic converter, these elements were likely forged in the neutron star collisions that were billions of years ago, which were scattered into a space by the explosions that were visible across the observable universe. We are quite literally made of the stellar catastrophes. But some of the neutron stars do not wait for the collisions to unleash their fury. The magnetars, the neutron stars with the magnetic fields that are trillions of the times stronger than the Earth's, occasionally experience the starquakes that crack their crusts and release more energy in the milliseconds than our Sun produces in the years. These giant flares create the short gamma-ray bursts that are detectable across the cosmic distances, the brief but the incredibly intense pulses of a high-energy radiation. The physics that were involved defy an everyday experience. A magnetar's magnetic field is so intense that it would be lethal to the humans at the distances of the thousands of the kilometers, not from a radiation, but from the magnetic field itself, which would interfere with the electrical activity in your nervous system. The field is strong enough to distort the shape of the atoms, creating the exotic states of a matter that exist nowhere else in the universe, except possibly in the cores of the neutron stars. When the magnetars flare, they briefly become the brightest objects in their local galactic neighborhoods. In a December of 2004, a giant flare from the magnetar SGR 1806-20 produced more energy in 1/10 of a second than our sun will generate over 100,000 years. The burst was so intense that it temporarily blinded the gamma-ray satellites and caused the detectable changes in the Earth's ionosphere, despite an originating 50,000 light-years away on the opposite side of our galaxy. Here is where the mathematics become genuinely unsettling. The computer models suggest that a magnetar's giant flare that is occurring within a roughly 30 light-years of the Earth could strip away a significant portion of our planet's ozone layer and exposing the surface to the lethal levels of an ultraviolet radiation. At the distances of 10 light-years or less, such an event might cause the mass extinctions that were comparable to the worst episodes in the Earth's geological record. Fortunately, we do not know of any magnetars in our immediate cosmic neighborhood. The nearest confirmed magnetar lies over 9,000 light-years away, which is uncomfortably close in a galactic term, but far enough that even a major outburst would pose no direct threat to the Earth. However, the neutron stars are notoriously difficult to detect unless they are actively emitting a radiation, and the astronomers estimate that there could be the billions of them that are scattered throughout our galaxy. And even more concerning are the long gamma-ray bursts, the death screams of the most massive stars in the universe. When a star that is more than 25 times the mass of our sun reaches the end of its life, it does not simply explode like an ordinary supernova. Instead, its core collapses directly into a black hole, launching the jets of a material at nearly the speed of a light. These jets, which are focused into the narrow beams by the extreme physics that are near the black hole's event horizon, create some of the most energetic explosions in the universe. The lethal distance for the gamma-ray bursts depends critically on their energy and their geometry, but an atmospheric modeling suggests that a burst that is occurring within the several thousand light-years of the Earth and is aimed directly at us could trigger a significant ozone depletion and a climate disruption. The burst itself would last only the seconds to the minutes, but its effects on the Earth's atmosphere could persist for the years. The terrifying aspect of the gamma-ray bursts is not just their energy output, it is their complete unpredictability. Unlike the supernovae, which can sometimes be anticipated based on the properties of their progenitor stars, the gamma-ray bursts appear to occur randomly throughout the universe with no advanced warning. The first indication of such an event would be the arrival of the gamma rays themselves, traveling at a light speed and providing a zero warning time. A modern gamma-ray astronomy has revealed that these cosmic catastrophes occur roughly once per day, somewhere in the observable universe, a sobering reminder of how violent and dangerous the cosmos really is. Fortunately, the beaming effects that make the gamma-ray bursts so energetic also work in our favor. The jets are typically only a few degrees wide, which means that even a relatively nearby massive star would need to be oriented with an extraordinary precision to pose a direct threat to the Earth. Most of the gamma-ray bursts sweep through an empty space, their deadly radiation that is dissipating harmlessly into the cosmic void. The detection network that is monitoring these cosmic giants has grown increasingly sophisticated. The NASA's Fermi Gamma Ray Space Telescope, the Swift Observatory, and the ground-based gravitational wave detectors like the LIGO, the Virgo, and the CAGRA work together to provide the real-time alerts when these cosmic catastrophes occur. Within the minutes of detecting a gamma-ray burst, the astronomers that are worldwide can point the optical and the radio telescopes toward the source, capturing the afterglow and learning about the physics of a stellar death. This multi-messenger approach has revolutionized our understanding of a cosmic violence. We are no longer limited to studying these events through a single type of radiation. We can observe them through the gravitational waves, the gamma rays, and optical light, and the radio emissions simultaneously building a complete picture of what happens when the universe unleashes its full fury. The frequency versus a consequence relationship for these cosmic giants provides both a comfort and a concern. The most energetic events, those that are capable of affecting the Earth from the great distances, are also the rarest. The magnetar's giant flares occur perhaps once per century in a typical galaxy. The nearby gamma-ray bursts that are capable of damaging the Earth's biosphere are estimated to occur only once every few hundred million years. Yet the universe is vast, containing the hundreds of the billions of the galaxies, each one of them, hosting the billions of the stars in the various stages of their life cycles. Somewhere in the observable universe, the neutron stars are colliding, the magnetars are flaring, and the massive stars are launching the gamma ray bursts toward the unseen targets. The fact that we can detect these events from the billions of the light years away is a testament both to their incredible energy and to the sophisticated instruments that we have developed to study them. What makes these cosmic giants particularly unsettling is their role as the cosmic arbiters of habitability. A sufficiently close and well-aimed gamma ray burst could sterilize the Earth's surface without a warning, resetting the evolutionary clock and forcing any surviving life to begin again from the simplest organisms. In this sense, these stellar phenomena serve as a kind of cosmic quality control, periodically cleansing the planets of complex life and ensuring that an intelligence remains a rare and precious commodity in the universe. But what if the next brilliant flash across our sky is not the collision of the distant neutron stars, but something that is far more violent? A star's final desperate scream as it tears itself apart in one last bid for an immortality. The hypothetical Doomsday 3, the false dawn star. Imagine awaking one morning to find the eastern horizon that is ablaze with a light that is not the sun. A false dawn stretches across the sky, casting the shadows in the wrong direction and painting the landscape in the colors that have no name. For a few terrifying seconds, this alien sunrise outshines the real one, which is visible even in a broad daylight, before fading to a brilliant point of a light that will haunt the sky for the months. You have just witnessed the death of a massive star and the birth of one of the universe's most terrifying phenomena. This is our third hypothetical doomsday scenario, a nearby massive star that is collapsing into a black hole and firing a gamma ray burst directly toward the Earth. While the odds of such an event are extraordinarily small, the consequences would be so catastrophic that even the seasoned astronomers occasionally lose sleep, contemplating the possibility. The gamma ray bursts represent the universe at its most violent. When a star that is more than 25 times the mass of our sun reaches the end of its life, its core can collapse so rapidly that not even a supernova explosion can halt the formation of a black hole. The infalling matter does not disappear quietly. It forms a superheated accretion disk that is around the newborn black hole and launching the jets of a material at 99.9% the speed of a light along the star's rotation axis. These jets carry more energy than our sun will produce over its entire 10 billion year lifetime, which is compressed into the beams that are only a few degrees wide. When one of these cosmic death rays sweeps across a space, it creates a gamma ray burst, an explosion that is so bright that it can be seen from the edge of the observable universe. The physics that were involved push the boundaries of what a matter and an energy can accomplish. The gamma rays themselves are the photons that are carrying the millions of the times more energy than a visible light. When they interact with the Earth's atmosphere, they do not create a gentle aurora. They trigger the nuclear reactions in the upper atmosphere, converting a nitrogen and an oxygen into the radioactive isotopes and destroying the ozone molecules that protect us from the sun's ultraviolet radiation. The computer models of this atmospheric destruction paint a sobering picture. A gamma ray burst that is occurring within a few thousand light years of the Earth and is aimed directly at us could deplete our ozone layer by 50% or more within a second. The immediate effects would be invisible to the human observers. The gamma rays do not create the spectacular light shows when they hit our atmosphere, but within the days or the weeks, the consequences would become apparent as the increased levels of an ultraviolet radiation began to reach the Earth's surface. The biological impact would unfold over the months to the years. Without an adequate ozone protection, an ultraviolet radiation would penetrate deeper into the ocean, disrupting the phytoplankton populations that form the base of the marine food chains. On a land, the increased UV levels would cause a widespread DNA damage in the plants and the animals, which is leading to the increased cancer rates and immune system suppression and the agricultural failures. The most vulnerable ecosystems, those that are already stressed by a climate change or a human activity, would face a potential collapse. But here is where the story becomes particularly unsettling. There would be no warning. Unlike the asteroid impacts, which we might detect the months or the years in advance, the gamma-ray bursts travel at the speed of a light. The first indication of such an event would be the arrival of the gamma rays themselves. The satellite-based gamma-ray detectors would register the burst within the milliseconds, but by then the damage to the Earth's atmosphere would already be underway. The false dawn effect would be genuinely terrifying for any humans who are witnessing it. For a few seconds to the minutes, a gamma-ray burst that is occurring within our galactic neighborhood would appear as a brilliant new star, potentially brighter than the full moon. The ancient astronomers would have interpreted such an event as a divine omen. The modern observers would know immediately that they were witnessing something that was unprecedented and potentially catastrophic. Historically, the astronomers have worried about the several candidate stars that might pose such a threat. The Wolf-Rayet 104, a massive star that is roughly 8,000 light-years away, once topped the list of the most likely to kill us all due to its enormous mass and a rapid rotation. However, the more recent observations have suggested that its rotation axis is not aligned with the Earth, which means that any gamma-ray burst that it produces would likely miss us entirely. This raises a crucial point about a gamma-ray burst's geometry. The beaming effect that makes these explosions so energetic also works in our favor. The jets are typically only 1 to 10 degrees wide, which means that even a relatively nearby massive star would need to be oriented with an extraordinary precision to pose a direct threat to the Earth. Most of the gamma-ray bursts sweep through an empty space, their deadly radiation that is dissipating harmlessly into the cosmic void. The timescales that were involved in the gamma-ray burst's effects span from the seconds to the centuries. The initial burst itself typically lasts anywhere from the milliseconds to the several minutes, a brief but an incredibly intense pulse of a high-energy radiation. The atmospheric chemistry effects would peak within the days, but could persist for the months or the years as the depleted ozone layer slowly recovered. The biological and the ecological consequences might unfold over the decades or the centuries. The current estimates suggest that the potentially lethal gamma-ray bursts occur in our galactic neighborhood roughly once every few 100 million years, which is frequent enough to have influenced the course of a life on the Earth over a geological time, but rare enough that a human civilization is unlikely to experience such an event. Some of the researchers have even proposed that the gamma-ray bursts might explain the certain mass extinction events in the Earth's geological record, though the evidence remains speculative. The detection and the monitoring of the massive stars has become increasingly sophisticated as the astronomers have come to understand the gamma-ray burst's threat. The space-based telescopes continuously monitor the known Wolf-Rayet stars and other gamma-ray bursts candidates, looking for the signs of an instability that might herald an impending collapse. The ground-based surveys search for the new candidates, while the theoretical models attempt to predict which stars are most likely to produce the Earth-threatening bursts. Yet even with an improved monitoring, the fundamental unpredictability of a stellar collapse means that the gamma-ray bursts will always retain an element of a cosmic roulette. We can identify the most likely candidates, but we cannot predict when or if they will explode. We can model the atmospheric effects with an increasing precision, but we cannot prevent them from occurring. The psychological impact of living with this knowledge is worth considering. How does it feel to know that somewhere in our galaxy, the massive stars are approaching the end of their lives, potentially carrying within them the power to reset a civilization? For most of the people, such threats remain comfortably abstract, too rare and unpredictable to influence daily decision-making. But for the astronomers who study these phenomena professionally, the knowledge can be genuinely unsettling. Perhaps the most disturbing aspect of the gamma-ray bursts scenario is its reminder of how little control we have over the cosmic phenomena that are operating on the scales that are far beyond human influence. We have developed the impressive capabilities for detecting and potentially deflecting the asteroid threats. We have mapped the locations of the nearby black holes and monitored the activity of our galactic center. But against a well-aimed gamma-ray burst, our technological civilization would be as helpless as the dinosaurs were against their cosmic impactor. The silver lining, if it can be called that, lies in the rarity and the randomness of such events. The universe contains the billions of the massive stars, but only a tiny fraction of them will ever produce the gamma-ray bursts, and an even smaller fraction of them will aim those bursts toward the inhabited planets. The cosmic lottery that governs a stellar death appears to be rigged in a favor of a survival most of the time. But what if the next existential threat does not come from the exploding stars or the colliding neutron stars? What if it emerges from the fundamental structure of a reality itself, a wave of a destruction that rewrites the laws of a physics as it passes? The hypothetical doomsday 4, the cosmic wave. In the realm of a speculative cosmic catastrophe, few scenarios are as simultaneously a fascinating and a terrifying as the possibility of a cosmic wave, a hypothetical disturbance in the fabric of a space itself that could fundamentally alter the laws of a physics as we know them. This is our fourth and most exotic doomsday scenario, a thought experiment that pushes the boundaries of a theoretical physics into a territory that would make even the science fiction writers to pause. Let's be absolutely clear from the start. There is no credible scientific evidence that is suggesting that such cosmic waves exist or pose any threat to the Earth. The scenario that we are about to explore exists purely in the realm of a speculative physics and a worst-case theoretical modeling. But the very fact that the reputable physicists have seriously considered such possibilities tells us something that is profound about how much we still do not understand about the universe that we inhabit. The concept emerges from our growing awareness of a dark energy, the mysterious force that appears to be accelerating the expansion of the universe. When the Albert Einstein first introduced his cosmological constant in 1917, he intended it as a static fudge factor to keep the universe from collapsing under its own gravity. He later called it his greatest mistake, when the observations revealed that the universe was actually expanding. But in 1998, the astronomers discovered that this expansion is accelerating, which is driven by some form of an energy that permeates all of space. A dark energy represents roughly 68% of the total mass energy content of the universe, yet we understand almost nothing about its true nature. Is it a fundamental property of a space itself? Is it a field that could potentially change a strength or a direction? Could it be unstable under the certain conditions? These questions push us into an uncharted theoretical territory where even our most sophisticated models provide a little guidance. One of the speculative possibilities that occasionally surfaces in a theoretical literature is the concept of a false vacuum decay. The idea that the quantum fields that define the fundamental properties of a matter and an energy might exist in a metastable state, like a ball that is balanced on the rim of a bowl rather than resting at the bottom. If such a system were disturbed perhaps by the quantum fluctuations or the interactions with the other fields that we have not yet discovered, it could theoretically trigger a cascade effect that would propagate outward at the speed of light. Such a wave would not be made of a matter or a conventional energy. It would represent a fundamental change in the underlying structure of a space-time itself, a region where the laws of a physics that are operating behind the wavefront would be fundamentally different from those that we observe today. The atoms might not be able to form, the fundamental forces might operate with the different strengths, and the very concept of a matter, as we understand it, might cease to have a meaning. The terrifying aspect of such a scenario is not the energy that was involved. It is the complete unpredictability of what would happen when the wave arrived. Would a matter simply cease to exist? Would it transform into the exotic forms that were governed by an alien physics? Would the conscious observers even be capable of perceiving the transition? Or would an awareness itself be impossible under the new physical regime? Fortunately, the same physics that makes such scenarios theoretically possible also suggests that they are extraordinarily unlikely to occur naturally. A quantum field theory indicates that the false vacuum decay events, if they occur at all, would be incredibly rare, perhaps once per universe per cosmic age. The energy barriers that are protecting our current vacuum state appear to be enormous, requiring the fluctuations that are far more extreme than anything that our current models predict. Moreover, our local observations of the cosmic microwave background radiation, the afterglow of the Big Bang, show no signs of the kind of the irregularities that might indicate a vacuum instability. The universe appears to be operating under the consistent physical laws across the billions of the light years of a space and the billions of the years of a time. If our vacuum state were genuinely unstable, we might expect to see an evidence of the decay events that are occurring in the distant regions of the observable universe. The concept of the cosmic waves also intersects with our understanding of the cosmic web, the large-scale structure of the universe that was revealed by the galaxy surveys and the computer simulations. On the scales of the hundreds of the millions of the light years, a matter is organized into the filaments and the sheets that are separated by the vast voids. The shock waves and the pressure fronts do propagate through this cosmic web as the galaxy clusters collide and merge. But these are the conventional phenomena that are involving the movement of a gas and a dark matter, not the fundamental changes to the laws of physics. Some of the speculative theories in a cosmology do allow for the more exotic possibilities. The brain world scenario suggests that our entire universe might exist as a membrane that is embedded in a higher dimensional space, potentially subject to the collisions or the interactions with the other brains that could fundamentally alter the physical laws. The string theory's landscapes propose the vast arrays of the possible vacuum states, each one of them with the different physical constants and the particle properties. But here is where a scientific responsibility becomes crucial. The boundary between a legitimate theoretical speculation and an unfounded fear-mongering can be surprisingly thin. The internet is filled with the claims about the imminent cosmic wave threats that are based on the misinterpretations of the legitimate scientific papers or the complete fabrications that are designed to generate the clicks and the views. Distinguishing between a peer-reviewed theoretical work and a YouTube cosmology requires a careful attention to the sources and a methodology. The scientific community has developed the several ways to test the stability of our current vacuum state. The particle accelerators like the Large Hadron Collider probe the behavior of the fundamental fields at the high energies, looking for the signs of an instability or the phase transitions. The cosmological observations monitor the cosmic microwave background and a large-scale structure for the anomalies that might indicate the vacuum decay events that are elsewhere in the universe. So far, all of the observations suggest that our universe is operating under the stable physical laws that have remained consistent across a cosmic time. The fundamental constants appear to be truly constant. The quantum fields that define the particle masses and the interaction strengths show no signs of an instability or a decay. If the cosmic waves of the type that we have been and imagining exist at all, they operate on the timescales and the distance scales that dwarf a human civilization. The psychological impact of contemplating such scenarios is worth acknowledging. There is something uniquely disturbing about the threats that attack the very foundation of a physical reality, rather than simply destroying a matter or an energy within the current framework. We can imagine surviving the asteroid impacts a radiation exposure and even a climate change, but it is difficult to conceive of an existence itself under the fundamentally different physical laws. Yet this discomfort also points to something that is positive about a human nature, our deep confidence in the stability and the comprehensibility of the universe that is around us. The fact that the cosmic wave scenarios feel so alien and threatening suggests that we have evolved in a genuinely stable cosmic environment, one where the laws of physics have remained consistent long enough for the complex structures like the galaxies, the stars, the planets, and a life to emerge and to persist. The ultimate lesson of a cosmic wave speculation might be one of a cosmic humility. Despite the centuries of scientific progress, we still understand only a fraction of what governs the universe at its deepest levels. A dark energy remains a mystery. A quantum gravity eludes our best theoretical efforts, and the relationship between a consciousness and a physical law remains completely opaque. But perhaps that is exactly why we should be grateful rather than terrified. The universe has provided us with a stable platform for an existence, a discovery, and a wonder. The laws of physics have remained consistent long enough for an intelligence to emerge and to begin asking the questions about its own existence. Whatever cosmic waves might theoretically exist in the vast spaces that are between the galaxies, they have not yet reached our corner of spacetime. In the end, the most honest response to the cosmic wave scenarios is not a fear, but an awe, an awe at the complexity and the subtlety of the universe that we inhabit, and a gratitude for the remarkable stability that has allowed us to exist long enough to contemplate our own cosmic situation. If the universe were truly unstable at the fundamental levels, we would not be here to worry about it. But if the fabric of a space-time is not hunting us, and if the laws of a physics remain stable and benevolent, then perhaps the greatest threats to our survival come not from a hostile cosmos, but from the other forms of an intelligence that have learned to navigate the cosmic dangers far better than we have. The Fermi Paradox. In 1950, during a casual lunch conversation at the Los Alamos National Laboratory, the physicist Enrico Fermi posed a question that continues to haunt the astronomers and the philosophers today. Where is everybody? His reasoning was deceptively simple. The universe is roughly 13.8 billion years old and contains the hundreds of the billions of the galaxies, each one of them hosting the hundreds of the billions of the stars. Even the conservative estimates suggest that the billions of the planets should be capable of supporting a life. So where are all of the aliens? This apparent contradiction between the high probability of an extraterrestrial intelligence and our complete lack of an evidence for it has become known as the Fermi Paradox. It is not really a paradox in the mathematical sense. It is more of a profound puzzle that forces us to confront the uncomfortable possibilities about our place in the cosmic order. Are we alone? Are we early? Are we being avoided? Or are we simply looking in the wrong places with the wrong tools? The numbers that were involved are staggering. Our galaxy alone contains roughly 400 billion stars, and the recent discoveries by the Kepler Space Telescope and other planet-hunting missions suggest that the Earth-sized planets in the habitable zones of their stars are surprisingly common. The conservative estimates indicate that there could be the billions of the potentially habitable worlds in the Milky Way alone, and expand that to the observable universe with its estimated 2 trillion galaxies, and the numbers become almost meaningless in their immensity. Yet despite the decades of searching, we have found no definitive evidence of an extraterrestrial intelligence, no radio signals that could not be explained by the natural phenomena, no mega-structures that were blocking the light of the distant stars, and no obvious signs of an industrial activity in the nearby star systems. The universe appears to be conspicuously quiet, a cosmic library with no other readers. The silence takes on the 2 distinct flavors, each one of them with its own troubling implications. First, there is the absence of a visitation, the fact that no alien spacecraft have landed on the White House lawn, despite what the tabloid headlines might suggest. Second, and perhaps more puzzling, is the absence of the detectable signals, or the signatures of a technological civilization anywhere in our cosmic neighborhood. Our search capabilities, while they are impressive by the historical standards, remain quite limited. The Search for Extraterrestrial Intelligence SETI project has examined only a tiny fraction of the nearby stars, and only within the narrow frequency bands that we assume might be favored for an interstellar communication. We are essentially trying to eavesdrop on the cosmic conversations by using the techniques that were barely more sophisticated than those that were available to the Marconi at the dawn of a radio. The advanced civilizations might communicate by using the methods that we have not even imagined yet. The temporal dimension of the Fermi Paradox adds another layer of complexity. A human civilization has been technologically advanced for only a few centuries, a cosmic eye blink. A radio astronomy has existed for less than a century. We have been actively searching for the extraterrestrial signals for only a few decades. If the technological civilizations are short-lived, lasting only the centuries or the millennia before destroying themselves or transcending their technological phase, then the chances of the 2 civilizations that are overlapping in both a space and a time become vanishingly small. Consider the vast scales that were involved. A light from the nearest star takes over 4 years to reach us. A radio signal from the galactic center would require 26,000 years to cross the space that is between there and here. If an alien civilization had been broadcasting a "Hello Universe" message when the Egyptian pyramids were being built, that signal would just now be reaching the star systems that were 5,000 light years away. The universe operates on the timescales that make a civilizational overlap seem almost impossible. This leads to what the researchers call the Great Filter Hypothesis, the idea that there is some evolutionary or a technological barrier that prevents most of a life from a developing into the detectable spacefaring civilizations. The filter might be behind us. Perhaps the emergence of a life itself, or the development of the complex cells, or the evolution of an intelligence is far rarer than we assume. Alternatively, the filter might lie ahead. Perhaps the technological civilizations inevitably destroy themselves through a war, an environmental collapse, or other catastrophes before they become detectable on the cosmic scales. The possibility that the Great Filter lies ahead of us is particularly unsettling. If an intelligence inevitably leads to a self-destruction, then our current technological capabilities might represent not the beginning of a cosmic conversation, but the final chapter of a terrestrial intelligence. Every nuclear weapon that we build, every degree of a warming that we add to our climate, and every potentially dangerous technology that we develop could be the steps toward the same fate that has silenced the countless other civilizations. But there are the other possibilities that do not require an assuming a civilizational suicide. Perhaps the advanced civilizations deliberately choose to remain quiet, recognizing that in announcing their presence might attract an unwanted attention from the hostile neighbors. Perhaps they have transcended the need for an electromagnetic communication, developing the technologies that operate through a quantum entanglement, or other phenomena that we have barely begun to understand. Perhaps they are already here and observing us with such a sophisticated camouflage that we cannot detect their presence. The search strategies that were employed by a modern SETI research have evolved far beyond simply listening for the radio signals. The astronomers now look for the techno-signatures, the indirect evidence of a technological activity that might be visible across the interstellar distances. These include the searches for the artificial structures that might partially block the light from the stars, an analysis of the exoplanet atmospheres for the industrial pollutants, and a monitoring for the brief laser pulses that might represent the interstellar communication attempts. The recent focus on the fast radio bursts, the mysterious millisecond pulses of a radio energy from the distant galaxies, illustrates both the promise and the frustration of a modern SETI work. When these signals were first discovered, some of the researchers speculated that they might represent an alien technology. A more detailed analysis has revealed that they are almost certainly the natural phenomena, likely produced by the highly magnetized neutron stars that are called the magnetars. But the fact that we seriously considered the artificial origins shows how desperately we want to find an evidence that we are not alone. A bias toward an anthropocentric thinking might be limiting our search strategies. We look for the kinds of the signals that we might send by using the technologies that we understand and operating on the timescales that seem to be reasonable to us. But the advanced civilizations might communicate by using the gravitational waves and manipulate a matter at the quantum scale, or operate on the geological timescales that make our entire recorded history seem like a brief moment of a noise. The Drake equation, which was formulated in 1961 to estimate the number of the communicating civilizations in our galaxy, remains more of a philosophical framework than a predictive tool. Its variables, the rate of a star formation, the fraction of the stars with the planets, the likelihood of a life that is emerging, are still poorly constrained despite the decades of an astronomical progress. Depending on which estimates you plug into the equation, you can derive the results that are ranging from "we are probably alone in the universe" to "there should be the millions of the detectable civilizations." Perhaps the most profound implication of the Fermi paradox is not about the aliens at all, it is about us. The apparent silence of the universe places an enormous responsibility on a human civilization. If an intelligence is as rare as the evidence suggests, then we might represent something that is genuinely precious in the cosmic order, a brief flowering of a consciousness in an otherwise unconscious universe. This responsibility cuts both of the ways. On the one hand, it suggests that a human civilization and the intelligence that it represents might be worth preserving at almost any cost. On the other hand, it raises the terrifying possibility that we are approaching the same filter that had silenced all of those other potential civilizations. Every global crisis that we face, a climate change, a nuclear proliferation, an artificial intelligence development, and a biotechnology's risk takes on a cosmic significance when it is viewed through the lens of the Fermi paradox. The paradox also forces us to confront the possibility that a consciousness itself might be far rarer and more fragile than we instinctively assume. We take our own awareness for granted, but the emergence of a subjective experience from a complex information processing remains one of a science's deepest mysteries. If a consciousness is indeed rare in the universe, then its preservation becomes a cosmic imperative. The recent developments in astrobiology have added the new dimensions to the Fermi paradox. The discovery of the potentially habitable exoplanets like the Proxima Centauri b, the TRAPPIST-1e, and the Kepler 452b has shown that the Earth-like worlds exist in our cosmic neighborhood. The James Webb Space Telescope's ability to analyze the exoplanet atmospheres will soon tell us whether any of these worlds show the signs of a biological activity. But even if we find a life, the question of an intelligence will remain. The search for an extraterrestrial intelligence continues to evolve and to expand. The new radio telescope arrays like the Square Kilometer Array will provide an unprecedented sensitivity to the artificial signals. The optical SETI searches monitor the millions of the stars for the brief laser pulses. The Breakthrough Listen initiative has brought a Silicon Valley's funding and an expertise to the search for the cosmic companions. Yet with each passing year of a silence, the Fermi paradox becomes more puzzling rather than less. Either we are extraordinarily alone, extraordinarily early, or extraordinarily blind to the signs of an intelligence that is around us. Each possibility carries the profound implications for how we understand our place in the universe and our responsibility to the future. But what if the silence itself is the answer? What if the advanced civilizations have learned that the universe is far more dangerous than it appears and that a survival requires something that we have not yet mastered, the discipline of a cosmic invisibility? The Dark Forest Hypothesis. In the Liu Cixin's acclaimed science fiction trilogy, The Three-Body Problem, a humanity's first contact with an extraterrestrial intelligence comes with a chilling warning: do not answer, do not answer, do not answer. The message comes from an alien pacifist who is desperately trying to prevent the Earth from revealing its location to a galaxy that is full of the predators. This fictional scenario encapsulates one of the most unsettling proposed solutions to the Fermi paradox, the Dark Forest Hypothesis. It was named after the second volume in the Liu's trilogy, and the Dark Forest Hypothesis suggests that the universe is indeed teeming with the intelligent civilizations, but they all remain silent out of an abundance of caution. Like the hunters that are moving carefully through a dark forest, each civilization knows that the others exist, but dares not to reveal its own position, because the first rule of a cosmic survival is a simple: any civilization that is capable of an interstellar travel is also capable of an interstellar destruction. The logic is coldly game theoretic. When the two civilizations encounter each other across the interstellar distances, each one of them faces a fundamental uncertainty about the other's intentions. Even if the alien civilization appears to be peaceful, there is no way to guarantee that it will remain so across the centuries or the millennia that are required for a meaningful interstellar interaction. The technological capabilities grow exponentially, and a civilization that poses no threat today might develop the planet-killing weapons tomorrow. Moreover, there is no reliable way to communicate the peaceful intentions across the interstellar distances. Any signal that is strong enough to cross a space could also serve as a targeting beacon. Any technology that is capable of propelling the spacecraft to the other stars could also propel the weapons. In this framework, the safest assumption is that any detected civilization represents a potential existential threat that should be eliminated before it can eliminate you. This creates what the researchers call a cosmic Cold War, a universe where every civilization that is capable of an interstellar travel maintains a strict operational security, a monitoring for the signs of the other civilizations, while revealing as little as possible about themselves. A detection equals a death, so a survival requires a perfect stealth across the cosmic timescales. The hypothesis gains an unsettling credibility when we consider the Earth's own behavior. For the past century, we have been, and inadvertently, broadcasting our presence to the galaxy through the radio and the television transmissions, the radar signals, and other electromagnetic radiation. Our planet glows like a beacon in the certain radio frequencies and announcing to anyone who is listening that the Earth hosts a technological civilization. But are we wise to be so conspicuous? The debate over a MITI messaging to extraterrestrial intelligence illustrates the tensions that are inherent in the dark forest scenario. Since the 1970s, the humans have occasionally transmitted the deliberate messages toward the nearby star systems, which are including the mathematical concepts, the cultural information, and even the musical compositions. The Arecibo message that was broadcast in 1974 toward the globular cluster M13 will arrive at its destination in a roughly 25,000 years. The critics of a MITI argue that we are essentially sending our cosmic address to the unknown recipients who might not have our best interests at heart. The proponents counter that our inadvertent radio leakage has already announced our presence, so a deliberate messaging adds a little an additional risk. But the dark forest hypothesis suggests that both of the perspectives might be dangerously naive, that in a universe that is full of the hidden civilizations, any form of a conspicuous behavior could be suicidal. The mathematics of an interstellar warfare support these grim calculations. A civilization that is capable of accelerating the spacecraft to the significant fractions of a light speed possesses the technology to deliver the kinetic weapons with a devastating effect. A simple probe that is traveling at 10% of a light speed would impact with the energy of the thousands of the nuclear weapons. At the relativistic speeds, even the small objects become the planet killers. The detection technologies follow the similar exponential curves. A civilization that is capable of building the radio telescopes that are much larger than our current instruments could detect the Earth's broadcast emissions from the hundreds of the light years away. The more advanced civilizations might monitor the gravitational waves, the neutrino emissions, or the exotic signatures that we have not even imagined yet. In the dark forest scenario, the watchers are always ahead of the watched. The hypothesis also explains the several puzzling aspects of the Fermi paradox. Why do we not see the obvious signs of a galactic engineering or a megastructure construction? Because the civilizations that build the conspicuous monuments to their technological prowess do not survive long enough to become the galactic civilizations. Why do we not detect an industrial waste heat or an atmospheric pollution on the exoplanets? Because the advanced civilizations either hide their signatures or eliminate the civilizations that fail to hide theirs. And even more disturbing is the possibility that the Earth is already being observed by the hidden civilizations that are waiting to see what we become. In this scenario, our planet represents a kind of a cosmic exam, a test of whether a human civilization can mature into a responsible galactic citizen or whether we will follow the path of an aggressive expansion that characterizes most of the failed civilizations. The recent focus on the interstellar objects like the ʻOumuamua takes on the sinister overtones when it is viewed through the dark forest's lens. While a mainstream astronomy treats these visitors as the natural phenomena, the comets or the asteroids from the other star systems, the hypothesis suggests that they might represent something that is far more ominous, the scout probes from the civilizations that are monitoring our development. Their unusual characteristics, which are including the ʻOumuamua's non-gravitational acceleration and a cylindrical shape, would be consistent with the artificial objects that were designed for a reconnaissance. Similarly, the growing catalog of the unexplained atmospheric phenomena, which are including the military's acknowledgement of the unidentified aerial phenomena that exhibit the flight characteristics that are beyond a current human technology, might represent an evidence that we are already being studied by the civilizations that are following the dark forest's protocols. They observe but do not interact, gathering an intelligence while maintaining a plausible deniability. The implications for human behavior are profound. If the dark forest hypothesis is correct, then our species faces a stark choice to learn a cosmic stealth and to join the galactic community of the hidden civilizations, or to continue broadcasting our presence and a risk in elimination by the more cautious neighbors. The window for making this choice might be narrower than we think. The other civilizations might interpret our current level of the radio emissions as an evidence that we are too immature or reckless to be allowed to develop the interstellar capabilities. Some of the researchers have proposed that humanity should immediately cease all of the high-power radio transmissions and implement a planetary radio discipline to reduce our electromagnetic signature. Others argue that it is already too late, that our radio emissions from the past century have created an expanding sphere of a detectability that now encompasses the hundreds of the nearby star systems. The psychological impact of accepting the dark forest hypothesis is genuinely unsettling. It suggests that the universe is not a vast, empty stage that is waiting for a cosmic civilization to flourish, but a dark ocean that is teeming with the predators where the slightest disturbance can attract a fatal attention. Every radio telescope that we build, every deep space probe that we launch, and every attempt to contact an extraterrestrial intelligence becomes a potential death warrant for our species. Yet the hypothesis also offers a strange form of a hope. If it is correct, then the universe is indeed full of an intelligent life. We are just not allowed to see it until we prove ourselves to be worthy of a membership in the galactic community. The silence that we observe might not represent a cosmic loneliness, but a cosmic discipline, a universe that is full of the civilizations that have learned the hardest lesson of all. Sometimes a survival requires an invisibility. The question that keeps the astronomers awake is not whether the other civilizations exist, it is whether they have learned to hide so well that we will never find them. And more troubling still, have they already found us, the alien conspiracies and the hidden visitors? The line between a legitimate scientific inquiry and a conspiracy theory has never been thinner than it is today when discussing the possibility of the hidden alien visitors in our solar system. The recent years have brought a perfect storm of the genuinely puzzling astronomical discoveries, the official government acknowledgments of the unexplained phenomena, and an internet ecosystem that amplifies a speculation faster than a peer review can sort a fact from a fiction. Consider the case of the ʻOumuamua, the first confirmed interstellar object to visit our solar system. When the astronomers discovered this cigar-shaped visitor in 2017, it initially appeared to be a straightforward, if an exciting example of a natural debris from another star system. But as the observations accumulated, the ʻOumuamua began to display a behavior that challenged the conventional explanations. The most troubling was its non-gravitational acceleration. The object was speeding up in the ways that could not be explained by the gravitational influences of the Sun and the planets alone. For the natural comets, such an acceleration is a routine which is caused by the jets of a vaporizing ice that create the tiny rocket effects. But the ʻOumuamua showed no signs of the gas and the dust clouds that typically accompany the active comets. It was an accelerating like a comet while looking like an asteroid. Into this gap that was between an observation and an explanation stepped some of the genuinely speculative ideas. The Harvard astronomer Avi Loeb proposed that the ʻOumuamua might represent an artificial technology, specifically a light sail, that was pushed by a radiation pressure from the sun. His calculations showed that an object with the right geometry and a composition could indeed exhibit the ʻOumuamua's observed acceleration through the purely artificial means. The scientific community's response was swift and largely skeptical. The alternative explanations emerged. Perhaps the ʻOumuamua was composed of a solid hydrogen that was sublimating invisibly, or maybe it was a fragment of a disrupted planet with the unusual thermal properties. The European Space Agency's official analysis concluded that a natural outgassing remained the most plausible explanation, even if the gas was not visible in the Earth-based telescopes. Yet the controversy that was surrounding the ʻOumuamua illustrates a broader challenge in a modern astronomy. How do we distinguish between the genuinely anomalous phenomena that deserve a serious investigation and the sensationalized claims that mistake the natural processes for an artificial intelligence? The answer lies in the quality and the quantity of an evidence, the rigor of an analysis, and the willingness to accept the mundane explanations, even when the exotic alternatives might seem to be more exciting. 2 years after the ʻOumuamua's departure, the solar system received another interstellar visitor, the comet Borisov. This object behaved exactly as the astronomers had expected, displaying a normal coma and a tail and outgassing at the predictable rates and following a trajectory that was consistent with a natural gravitational mechanics. The Borisov served as a perfect control experiment, demonstrating that the interstellar objects can and do behave according to the well-understood physics. The arrival of the 3-Eye Atlas in 2025 has renewed these debates. Like the ʻOumuamua, this latest interstellar visitor has generated its share of speculation, particularly regarding its green coloration. The social media posts have breathlessly described it as an alien craft or an extraterrestrial probe. But the reality is far more prosaic. That eerie green glow almost certainly comes from the same diatomic carbon fluorescence that colors many of the ordinary comets, a natural phenomenon that is caused by a solar radiation that is energizing the simple molecules in the object's coma. The challenge for both the scientists and the public is maintaining an appropriate skepticism while remaining open to the genuinely revolutionary discoveries. The universe is vast and strange, and it is entirely possible that some of the astronomical phenomena might eventually prove to be artificial in an origin. But an extraordinary claim requires an extraordinary evidence, and that evidence must meet the rigorous scientific standards. This becomes particularly important when we consider how the alien visitation claims proliferate in the digital age. A single unusual observation can spawn the dozens of the YouTube videos, the blog posts, and the social media threads, each one of them amplifying the speculative interpretations, while often ignoring the more mundane explanations. The result is a kind of an information ecosystem where the sensational claims spread faster than a careful analysis can debunk them. The recent military's acknowledgement of the unidentified aerial phenomena, the objects that are displaying the flight characteristics that exceed a known human technology, has added another layer of complexity to these discussions. While the defense officials have been careful to avoid claiming these phenomena are extraterrestrial, in an origin the mere admission that the military sensors have detected the objects that are behaving in the inexplicable ways has energized a speculation about a hidden alien presence on the Earth. If the extraterrestrial civilizations were conducting a surveillance of the Earth, then what would that surveillance look like? The dark forest hypothesis suggests that the advanced civilizations would prioritize stealth above all else, using a technology so sophisticated that their probes would be essentially undetectable by the primitive civilizations like ours. Such probes might masquerade as the natural objects, the asteroids, the comets, or even the mundane space debris, while gathering an intelligence about a human technological development. The physics of an interstellar probe's design supports this possibility. A sufficiently advanced civilization could construct the surveillance devices that were small enough to avoid an easy detection, while powerful enough to monitor an entire planet's electromagnetic emissions. These probes might be entirely passive, collecting data without transmitting anything that could reveal their artificial nature. They could remain in our solar system for the decades or the centuries, studying a human civilization while remaining completely hidden. From this perspective, every unusual astronomical object becomes potentially suspicious. Could some of the near-Earth asteroids be the disguised alien artifacts? Might some of the comets be carrying the hidden sensors along with their natural ice and a rock? Are there the monitoring stations that are hidden among the Trojans at the Jupiter's Lagrange points, or camouflaged as the ordinary Kuiper belt objects in the outer solar system? The uncomfortable truth is that the current astronomical surveys are not designed to detect such objects, even if they exist. We catalog the asteroids and the comets based on their orbits and the basic physical properties, but we rarely examine them in the kind of detail that might reveal the artificial components. A sufficiently sophisticated probe could easily hide among the millions of the small bodies in our solar system, which are indistinguishable from natural debris, until they are subjected to a close inspection. This creates a troubling epistemic problem. An absence of an evidence is not an evidence of an absence. The fact that we have not definitively detected the alien probes in our solar system does not prove that they are not there. It might simply mean that they are better at hiding than we are at seeking. Every natural explanation for the unusual phenomena, like the Oumuamua's acceleration, might be correct, but it might also represent a successful camouflage by an intelligence that is far more advanced than our own. The implications extend beyond a pure science into the questions of a planetary security and a human autonomy. If the Earth is indeed under a surveillance by a hidden extraterrestrial intelligence, then what are the Watchers learning about us? Are they studying our technology, our biology, and our social structures? Are they simply gathering data? Or are they preparing for some form of a contact or an intervention? These questions resist the easy answers because they operate at the intersection of a legitimate scientific inquiry and an unavoidable speculation. The tools of a science work well for studying the natural phenomena that follow the consistent physical laws, but they are less effective at detecting an intelligence that might be actively trying to avoid a detection. We are essentially playing a cosmic game of a hide and seek, where we do not know the rules, the number of the players, or even whether the game is actually being played. The responsible approach lies in a continued rigorous observation that is combined with a healthy skepticism about the exotic explanations. Every anomalous object deserves a careful study, but an extraordinary claim requires an extraordinary evidence. The universe is strange enough without invoking an alien intelligence to explain every puzzling observation. Yet we should also remember that the absence of the confirmed extraterrestrial visitors does not mean that we are necessarily alone. The galaxy might be full of the civilizations that are simply better at staying hidden than we are at finding them. In a universe that is governed by a dark forest's logic, the most successful civilizations might be the ones that we never see at all. But what if some of the signals are so strange, so persistent, and so clearly artificial in an origin that the natural explanations begin to strain credibility? What happens when the universe refuses to stay silent? In the catalog of the cosmic mysteries that refuse to yield to a conventional explanation, few phenomena have generated as much an excitement and a frustration as the fast radio bursts. These millisecond duration flashes of radio energy, which were first discovered in an archive data from 2007, seem to arrive from the random directions in a space with no obvious natural explanation. For the years, they represented one of astronomy's most tantalizing puzzles, a brief brilliant and an utterly alien. The mystery began with a single burst that was detected in data from the Parkes radio telescope in Australia, lasting only 5 milliseconds, but releasing as much energy in the radio waves as the sun produces in an entire day. The signal appeared to come from a galaxy that was billions of light years away, its frequency characteristics that were suggesting that it had traveled through the vast amounts of an ionized gas, confirming its extragalactic origin, but providing no clues about what could produce such an intense brief flash of radio energy. For the years, the fast radio bursts existed in a kind of scientific limbo. Were they the natural phenomena that were involving the exotic stellar processes? Were they the instrumental artifacts or a terrestrial interference that were masquerading as the cosmic signals? Or could they represent something that was genuinely artificial? Perhaps the signatures of the advanced civilizations that were using the focused radio beams for an interstellar communication or propulsion. The artificial intelligence hypothesis gained traction among some of the researchers for the compelling reasons. The burst's extreme brightness and a brief duration seem to be more consistent with the engineered signals than the natural processes. Their apparent random distribution across the sky suggested that they might originate from the many different sources rather than a single type of cosmic object. The most intriguingly, some of the bursts appeared to repeat, which seemed to be difficult to reconcile with the catastrophic stellar events, but consistent with a technology that could be activated the multiple times. Then, in 2020, the mystery received its first major breakthrough. A fast radio burst was detected that was coming from within our own galaxy, specifically from the SGR 1935 Plateau 184, a known magnetar that was located roughly 30,000 light-years from the Earth. This single observation revolutionized the field, proving conclusively that at least some of the fast radio bursts have the natural origins. The magnetars are the neutron stars with the magnetic fields that are trillions of the times stronger than the Earth's, the objects that are so extreme that they exist at the very limits of what a matter can withstand. When these stellar remnants experience the starquakes, the fractures in their incredibly dense crusts, they can release more energy in the milliseconds than our sun produces in the years. The magnetic fields channel this energy into the focused beams that sweep across the space like the cosmic lighthouses. The galactic fast radio burst was not just a scientific vindication of the natural explanations, it was also a sobering reminder of the universe's capacity for a violence. The energy release was so intense that it temporarily disrupted the Earth's ionosphere, despite an originating 30,000 light-years away. If a similar event had occurred within a few hundred light-years of the Earth, it might have caused a significant damage to our technological infrastructure and potentially to our biosphere. But the pulsar-magnetar explanation, while it is compelling for many of the fast radio bursts, does not solve every mystery. The population of the observed bursts shows a remarkable diversity in their properties. Some of them repeat, and others are the one-time events. Some of them show the complex frequency structures, and others are relatively simple. Some of them appear to come from the active star-forming regions, and others from an apparently empty space. This diversity suggests that the multiple physical processes might be responsible for creating these cosmic flashes. The story becomes even more complex when we consider the other persistent cosmic anomalies that continue to defy an easy explanation. The famous WOW signal that was detected by the Big Ear radio telescope in 1977 remains one of astronomy's greatest unsolved mysteries. A lasting 72 seconds and displaying the characteristics that were consistent with an artificial origin, the signal appeared once and was never detected again, despite the decades of the follow-up observations. The recent attempts to explain the WOW signal have focused on the rare natural phenomena, perhaps the reflection of the Earth-based radio emissions off a cloud of the hydrogen atoms, or the emissions from a comet whose hydrogen coma was unusually dense. But these explanations remain speculative, and the signal's precise frequency, duration, and failure to repeat continue to puzzle the researchers more than 4 decades after its detection. Similarly, the KIC 8462852, which is better known as the Tabby's star, created a sensation in the astronomical community when the citizen scientists discovered its bizarre pattern of the brightness variations. The star would randomly dim by up to 22%, which was far more than could be explained by the typical stellar processes or the planetary transits. An initial speculation focused on the alien megastructures, perhaps the massive solar collectors or the habitat rings that were constructed by an advanced civilization. The subsequent observations have largely deflated the alien megastructure hypothesis. The star's dimming appears to be wavelength dependent, which suggests a dust or debris rather than the solid structures. The most likely explanation involves the clouds of the comet fragments or the asteroid debris that are periodically blocking the star's light. But the precise mechanism remains unclear, and the Tabby's star continues to behave in the ways that challenge our understanding of the stellar systems. These cases illustrate both the promise and the peril of an anomaly-driven astronomy. The unusual observations often point toward the genuinely new physics or the previously unknown astrophysical processes. The discovery of the pulsars in 1967 initially generated a speculation about the artificial little green men signals before revealing the existence of the neutron stars, the objects that were so extreme that they had been considered theoretically impossible. Similarly, the gamma-ray bursts were mysterious for the decades before we understood that they represented the most violent explosions in the universe since the Big Bang. The challenge lies in distinguishing between the genuinely revolutionary discoveries and the more mundane phenomena that are masquerading as the cosmic mysteries. Our pattern-seeking brains are exquisitely adapted to finding the signals in a noise, but this same capability can lead us to see an artificial intelligence where only the natural processes exist. The key is maintaining what the Carl Sagan had called the fine line between a skepticism and a wonder, remaining open to an extraordinary discovery while demanding an extraordinary evidence. A modern survey like the Zwicky Transient Facility and the upcoming Vera C. Rubin Observatory promise to revolutionize our ability to detect and to study the cosmic anomalies by monitoring the millions of the stars simultaneously. These facilities will catch the rare events that the previous surveys might have missed. The computer algorithms will automatically flag an unusual behavior and allowing the astronomers to respond quickly with the follow-up observations. But this flood of new data will also present the new challenges. Every survey that becomes more sensitive discovers the new types of the cosmic transient phenomena, most of them natural, but some of them a potentially artificial. A distinguishing between the two will require not just the better instruments, but the better theoretical frameworks for an understanding what kinds of the signatures the advanced civilizations might produce. The search for the genuine technosignatures, the unambiguous evidence of an extraterrestrial technology, continues to evolve beyond the simple radio signals. The astronomers now monitor for an infrared excess that might indicate the Dyson spheres, look for the laser pulses in an optical data, and search for the artificial transit patterns that might reveal the megastructures. Each new survey technique opens the possibilities for both a discovery and a disappointment. Perhaps most importantly, these cosmic anomalies remind us that the universe still holds the profound mysteries that resist an easy categorization. Whether they ultimately prove to be the natural phenomena or something more exotic, they represent the genuine puzzles that push the boundaries of our understanding. In a cosmos that can produce the neutron stars, the black holes, and a dark energy, perhaps we should not be surprised that some of the phenomena continue to challenge our theoretical frameworks. The uncomfortable truth is that we still understand only a fraction of what is happening in the universe that is around us. Every resolved mystery reveals the new questions, every explained anomaly points toward the deeper puzzles, and occasionally something appears in our data that does not fit any category that we have previously encountered. What happens when the noise in the cosmic background finally resolves into something that we cannot explain away? What if the next anomaly that we discover is not just unusual, but unmistakably artificial? As we reach the end of our journey through the cosmic catalog of dread, a paradox emerges that's more unsettling than any individual threat we've examined. The universe reveals itself to be simultaneously dangerous, beyond imagination, and mysteriously profoundly quiet. This silence, not the absence of sound, but the absence of obvious intelligence, might represent the most terrifying discovery of all. We've traveled from the ice mountains of the Oort cloud to the event horizons of black holes, from the gamma-ray screams of dying stars to the theoretical possibility of cosmic waves that rewrite reality itself. Each threat operates on scales that dwarf human experience, wielding energies that could erase our civilization in milliseconds. Yet for all their cosmic violence, these phenomena follow predictable physical laws. We can model them, track them, and in some cases prepare for them. But the silence surrounding us suggests something far more ominous than mere physical danger. It hints at a universe where intelligence itself might be the rarest and most fragile phenomenon of all, or where intelligence has learned lessons we haven't yet grasped about the price of visibility in a hostile cosmos. The trajectory of human planetary defense capabilities offers a glimpse of hope amid the catalog of cosmic terrors. From the dinosaur-killing Chicxulub impact 66 million years ago to NASA's successful DART mission in 2022, we've progressed from helpless victims to active participants in our own cosmic security. The Atlas and ZTF surveys scan the skies nightly, cataloging potentially hazardous objects with increasing precision. The upcoming Vera C. Rubin Observatory will revolutionize our ability to detect long-period comets and other threats years or decades before they pose a danger to Earth. Yet even our growing competence in planetary defense reveals uncomfortable limitations. We can nudge small asteroids off collision courses, but we remain essentially helpless against the cosmic giants we've imagined: the hypothetical Thanos and Leviathan comets, the rogue black holes drifting through interstellar space, the gamma-ray bursts that could sterilize our biosphere without warning. Against such forces, early detection becomes less about prevention and more about acceptance, the difference between dying with knowledge and dying in ignorance. The professional fears of astronomers reflect this fundamental asymmetry between cosmic threats and human capabilities. What keeps planetary defense experts awake at night isn't necessarily the known threats. We can calculate probabilities and prepare responses for asteroid impacts, solar storms, and other quantifiable dangers. It's the unknown unknowns that generate existential dread, the objects approaching from our blind spots, the phenomena we haven't yet learned to detect, the threats that operate according to physics we don't yet understand. This uncertainty extends beyond physical dangers to encompass the deepest questions about our place in the universe. Are we alone in a cosmos that generates intelligence rarely and sustains it briefly? Are we early arrivals in a universe that will eventually teem with consciousness? Or are we surrounded by civilizations that have learned the cosmic discipline of perfect silence? Each possibility carries profound implications for how we should conduct ourselves as a species. If we're alone, then human consciousness represents something genuinely precious, a brief flowering of awareness in an otherwise unconscious universe that deserves protection at almost any cost. If we're early, then we bear the responsibility of being the first intelligence to grapple with cosmic-scale engineering and the challenges of interstellar expansion. But if we're surrounded by hidden civilizations practicing dark forest discipline, then our current behavior might be catastrophically naive. Our radio emission space probes and attempts at interstellar communication could be painting a target on Earth for civilizations that have learned to fear any species foolish enough to announce its presence to the galaxy. The silence itself becomes a phenomenon worthy of study. Why don't we see obvious signs of galactic engineering? Why haven't we detected the waste heat signatures of Dyson spheres or other megastructures? Why do even the most sensitive radio telescopes fail to detect the chatter of interstellar commerce or the leakage from alien entertainment systems? Perhaps the answer lies not in the absence of intelligence, but in its abundance. A galaxy full of civilizations that have learned to remain invisible would look exactly like the universe we observe, apparently empty, but actually teeming with hidden activity. The most successful civilizations might be the ones we'll never detect until we prove ourselves worthy of contact through our own mastery of cosmic stealth. This interpretation transforms every aspect of human space exploration, from scientific endeavor to existential test. Are our deep space probes being monitored by unseen watchers? Do our radio emissions mark us as a primitive species not yet ready for galactic citizenship? Is human civilization undergoing some form of cosmic evaluation whose criteria and consequences remain hidden from us? The psychological weight of such possibilities can be overwhelming. It's one thing to fear asteroid impacts or gamma-ray bursts. At least these threats operate according to physics we can study and mathematics we can calculate. It's quite another to suspect that every choice we make as a species might be observed and judged by intelligence far more advanced than our own. Yet this uncertainty also provides a strange form of liberation. If the universe is indeed silent because its inhabitants have learned to be quiet, then the very existence of that silence proves that intelligence can survive and thrive on cosmic timescales. The absence of obvious galactic civilizations becomes evidence not of civilizational failure, but of civilizational success, intelligence that has matured beyond the need for conspicuous displays of technological prowess. In this framework, humanity's current situation resembles adolescence on a cosmic scale. We're old enough to build dangerous technologies and young enough to use them carelessly. We're sophisticated enough to detect some cosmic threats, but naive enough to broadcast our location to unknown listeners. We're intelligent enough to ask profound questions about our place in the universe, but not yet wise enough to fully comprehend the implications of the answers. The path forward requires a delicate balance between caution and curiosity, between cosmic paranoia and cosmic wonder. We must continue scanning the skies for threats while remaining open to the possibility that some of those threats might be avoiding detection as carefully as we should probably be avoiding broadcast. We need to develop better tools for distinguishing natural phenomena from artificial intelligence while preparing for the possibility that such intelligence might be deliberately mimicking natural processes. Perhaps most importantly, we must cultivate what might be called cosmic humility, a recognition that we're newcomers to a universe that has been operating according to its own logic for nearly 14 billion years. The rules of cosmic civilization, if they exist at all, were written long before Earth existed. Our survival might depend not on rewriting those rules, but on learning to follow them. The catalog of cosmic threats we've explored, from comet impacts to black hole encounters, from gamma-ray bursts to theoretical cosmic waves, represents more than just a survey of existential dangers. It's a meditation on humanity's precarious position in a universe that operates on scales and timescales that dwarf our everyday experience. We're biological creatures adapted for life on a single planet, trying to comprehend phenomena that span galaxies and eons. Yet we persist in this cosmic detective work because the alternative, remaining ignorant of our celestial environment, seems even more dangerous than knowledge itself. Every threat we identify and characterize becomes one less unknown in the vast catalog of cosmic possibilities. Every survey we complete, every model we refine, every defensive capability we develop marginally improves our species' odds of long-term survival. The silence of the universe surrounding us might represent cosmic loneliness or cosmic discipline. It might indicate that intelligence is rare beyond imagination or common beyond detection. It might mean we're the first to ask these questions or the last to answer them without catastrophic consequences. What terrifies scientists isn't just what we know about cosmic threats. It's the growing suspicion that what we don't know might be even more dangerous than what we do. In a universe that can hide entire civilizations behind veils of perfect stealth, that can harbor rogue black holes in the spaces between stars, that can unleash gamma-ray bursts without warning across galactic distances, our greatest fear might not be the monsters we can see approaching, but the ones that have learned to approach unseen. The question that will define our species' future isn't whether we're alone in the universe. It's whether we're wise enough to survive the answer, whatever it might be.